So in this video, we're going to attempt to relate the periodic table, which was developed just by looking at the physical and chemical properties of the elements, to the electronic structures of the elements, which was determined by looking at the quantum mechanical model of Schrödinger. And even though these two models and theories were developed at different points in time, if they're valid, there should be an agreement between what we see in both of these models. So if I look at the electron configuration of two elements like calcium and potassium, what I recognize is that they have some parts of their electron configuration in common. In particular, I see that their core electrons, the first 18 electrons that they have that I've highlighted here in yellow, all have the same electron configuration. Now, these core electrons are not as chemically interesting as the outer electrons, what we call the valence electrons. So what I can do is I can recognize that those first 18 electrons, the core electrons, are just the same as those that are found in argon. And then these electrons that are in the outer shell, in the fourth shell here, they're the ones that I want to focus my attention on. So what I'm going to do is I'm going to replace the electron configuration for the core electrons with just the symbol of argon, and in particular I'm going to put it in parentheses, and then after that I'm going to write the valence electrons. And that just kind of makes the electron configuration a little smaller and also focuses the attention on those chemically important valence or outer shell electrons. So this is what we're going to do. We're going to take those first 18 electrons and we're going to replace their electron configuration with the symbol for argon in square brackets. And then I can see immediately that potassium here has one valence electron in a 4s subshell. And similarly, calcium, which has 20 electrons, has 18 core electrons, which are in the electron configuration of argon, and then it has 2 valence electrons in the fourth shell. Alright, so we can kind of continue that for any element that we want to. What we're going to do is to write this sort of condensed or abbreviated form of the electron configuration is we're going to write the symbol that comes before the element that we're interested in. So in this case, it's going to be sodium. The symbol for the noble gas that comes before it, which is neon, and then we just add outer electrons until we get to the configuration that we're interested in. So sodium has 11 electrons, and 10 of them are in the configuration of neon, and then those guys are just the outer electrons there. Magnesium has a total of 12 electrons. 10 of them can be replaced with the symbol of neon, and then we just have to write the number of electrons that we have beyond the first 10. Boron, here it is here, has a total of 5 electrons. The noble gas that comes before it is helium. And so we write the symbol for helium, and then we just write that it needs another 3 electrons to finish off its configuration. So that is 2s2, 2p1. The same here with oxygen. The noble gas that comes before oxygen is also helium. So we write the symbol for helium, and then we write the remainder of the electron configuration. So it's not too bad, right? It's easy to take a full electron configuration and write it as the condensed or abbreviated electron configuration. So if I look at a series of elements that are in the same group, and in this case I'm looking at group 1a, is there anything that I notice about their electron configuration? Well, when I look down here, what I see is that all of these elements have an electron configuration that ends with 1 electron in an s subshell. The other thing that I notice is that the highest shell that I observe is equal to the period where I find that electron. So francium's in period 7 and its highest shell is 7. Cesium's in period 6 and its highest shell is 6. Rubidium is in period 5, and you guessed it, its highest shell is number 5. Potassium is in period 4, its highest shell is number 4. Sodium, 3, and so forth, right? So the highest shell is always equal to the period number. That's kind of cool. The other thing I notice here is that we always have one electron in an S subshell, right? They all end S1. So can we relate that to anything in the periodic table? Well, it's interesting to know that these are all in group 1A, or using the North American numbering system. They're all in, sorry, that's the IUPAC numbering. The North American numbering system, it's 1A for that group. So can we relate that to the electron configuration in any way? I guess they all have one outer electron, they all have one valence electron, so that's worth noting. Let's have a look for another group. This is group 5A. This is your nitrogen group, so it's nitrogen, phosphorus, arsenic, and antimony, and we see the same kind of thing. We've got 5 outer electrons in the second shell, and sure enough, they're in group 5A, and it's in period 2. For phosphorus, again, 5 electrons are in the third shell, and you guessed it, it's in period 3. So it does seem that the number of outer electrons is related to the group number, at least for the A groups, right? So let's try again for arsenic. Now it gets a little weird here. We have to add up the number of electrons in the outermost shell. There's 5, 2 plus 3. It gives me 5 electrons, and the outermost shell is the fourth shell, so that is, and when we look in the periodic table, arsenic is in period 4. And then again, we've got 5 plus another 3 in the fifth shell, so there are 5 electrons in the fifth shell, and sure enough, when I look on the period table, antimony is in period 5. So it looks like that the number of outer electrons is related to the group number, and the period is related to the outermost shell. So that's what we can see, and we see that for any of the A groups, that the total number of electrons in the outermost shell is always equal to the group number. So if I was to go over to the oxygen group, group 6A, I would expect them to all have an outermost shell with 6 electrons in it. If I go over to 7A, I would expect the outermost shell to have 7 electrons in it, and so on and so forth, right? So it becomes really easy from the periodic table to identify the number of outer electrons. So it definitely seems that the arrangement of the elements in the periodic table is directly related to the electron configuration as predicted by Schrödinger and other people that developed the quantum mechanical model. So that's really cool. Now, if we look at the periodic table and we consider its shape, and keep in mind that the periodic table was invented before we ever knew anything about protons, neutrons, or electrons, yet alone shells, subshells, and orbitals, we see that there's kind of like 4 main blocks to it. There's this block on the far left that is 2 groups across. There's this block on the far right that is 6 groups across. There is this block in the middle that is 10 groups across, and then there's this block underneath the periodic table that is 14 groups across. Now, where have we seen 2, 6, 10, and 14 before? Well, that is simply the number of electrons that it's possible to put into an S, P, D, and F subshell, respectively. So it seems as though the shape of the periodic table is related to the electron configuration of the elements. And so the periodic table is often thought of as belonging to, as being able to be divided into what we call blocks or areas. So in these first 2 columns on the far left, we're putting electrons into S subshells. And so this is referred to as the S block. Any element that's in the first row there has an electron configuration that ends S1. Any element that goes in the second row there has an electron configuration that ends S2. Over on the far right, we have what we call the p block. And the p block, you guessed it, any element there has electron configuration ending p1, p2, p3, p4, p5, and p6. And similarly, across the middle of the periodic table, we're in the d block. All of these guys, d1, all of these guys, d2, all the way across, dot, 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 dot. And those guys, their electron configuration, the very last row there ends d10. For the F block, the same. These guys are all F1, these guys are all F14, and so on as we go across. So the reason that the periodic table has this shape is because we have 2, 6, 10, and 14 electrons that we can put into each of the 4 different types of subshells. Remember, elements with a similar electron configuration are going to look the same on the outside and are going to behave chemically similar. So everything in group 1A behaves chemically similar because they have an electron configuration that ends similarly. It all ends with S1. Everything in the noble gases behaves chemically similar in that it doesn't do much because they all have an electron configuration that end P6, right? So that's what's going on there. So things in the same group have similar chemical properties because they have similar outer electron configurations, and it's through the outer electrons that atoms fill out their world and interact with other atoms. So we can always figure out what is the distinguishing electron, the electron that kind of gives it its properties, by considering where it is in the periodic table. As I said, this is always going to end S1, S2, this will always be D10. We can always really quickly figure out what that last electron is. Now we can go even better because we know that the period number indicates the highest shell. We can figure out what the exact subshell is that those last electrons are in. So this is period 6, so it's going to be the 6s1 here, 6s2 there. Now it's worth recognizing a couple of things, that the D subshell, the outermost D subshell, always lags one behind the period number, right? And similarly, the outermost F subshell always lags behind the period number by 2. So sometimes people call this the N-2 F block. All right, just to kind of keep that in mind, that it's going to be 2 lower than the period number, and they call this the N-1 D block to remind us that it's 1 behind the period number, whereas this will be the NS and this will be the NP. Can you see that? Right? So that's what's going on there. Now, of course, we don't get any F electrons until we get down to period 6 and 7. So now you can kind of use the periodic table if you want to count off an electron configuration instead of using the Aufbau diagram. So you can just go 1s1, 1s2, 2s1, 2s2, 2p1, 2p2, 2p3, 2p4, 2p5, 2p6, 3s1, 3s2, 3p1, 3p2, 3p3, 3p4, 3p5, 3p6, 4s1, 4s2, 3d1, and you just kind of keep going, and so forth, right? So it can be useful to count them off in that way, and having a little image like this can be an alternative to using the Aufbau diagram. Okay, so let's do it. So it says writing the electron configuration of a neutral atom with a filled D subshell. So I have to write a neutral atom, so I don't have to add or remove any electrons for zinc. So zinc, there we go, what's its atomic number? It's right there, 30. So I know that I've got 30 electrons. So let's number the periods. I always like to number it on the right hand side. 1, 2, 3, 4. So I know, because this is the N-1 D, that this is going to end, it's in period 4, it's going to end 3D10. Right, that's where it's going to end. So I always know where it's going to end. So I've got a couple of things that I can do now. I can count off the period off the Aufbau diagram until I get up to 30, or I could count off the periodic table until I get to zinc. So I'm going to do both ways. So 1s2, done. Next one is 2s2, done. 2p6, done. 3s2, done. So that gets me to 12, right? 3p6, 18, 4s2, 20, and then there I am there, 3d10, 30. So I know I got it right because it ends at 3d10. I got a total of 30 electrons. There's no possibility I made an error. Another way of doing this would be to count off the periodic table. So I would go 1s1, 1s2, and that's 4. 2s1, 2s2, that's 4. 3p1, 3p2, 3p4, 3p5, 3p1, 3p2, 3p3, 3p4, 3p5, 3p6. That gets to me to there. And 2p. 3s1, 3s2, that gets me to the end of that. And then we are 3p1, 3p2, 3p3, 3p4, 3p5, 3p6, that gets me to the end of that. And then we got 4s1, 4s2, that gets me to the end of the S block. And then 3d1, 3d2, 3d3, all the way up to 3d10. So it doesn't really matter what way I do it. I just got to remember that that's ns, that's n minus 1d, that's np, and then this is n minus 2f. So you can count them off the periodic table if you want to. Okay, so now it says writing the electron configuration of an atom using the periodic table. So then it says write the electron configuration of an atom of the element highlighted in this outline of the periodic table. So they kind of want you to do it without the symbol, right? Now, what I know is it's in the D block, and it's in period 4, and it's the first member. So it's going to be 3D1. That's where my electron configuration is going to end. So it goes 1s1, 1s2, 2s2, 2p6, 3s2, 3p6, gets me to there, 4s2, and then bingo, 3d1. And having a little periodic table that looks like this can help. It's important to remember that helium finishes off the first subshell, so that helium is 1s1, so 1s2, so it's kind of bucking the trend a little bit. Okay, let's have a look at another Alex type problem. It says identifying S, P, D, and F block elements. This is pretty easy because you're going to have available to you a diagram like this, and you just need to match the region. So it says in the period below, shade the P block elements. So here they all are, but there's only one little trick here, is we're not going to shade helium. Okay, just remember that. We're not going to shade helium. So helium is finishing off the 1s subshell. So that's fairly trivial. If they wanted the F block, it would be there. If we wanted the S block, it would be there, but we would have to remember to put in helium. Okay, so that concludes the final video for chapter 10. I think it's really cool. We take two things that are separated in time by about 60, 70 years, two different theories. The people that invented the periodic table had no idea about subatomic particles and the arrangement of electrons in atoms, but somehow they generated a table that totally lines up with what the quantum mechanical model predicts. So it's kind of cool in a sense, right? It works the way that science should work. One thing builds on the other. Okay, if you have any trouble with the content, please don't be afraid to reach out to me.